So welcome everyone. So today we are going to have an exam review session, right? So we are going to see 2022 exam question papers, right? And we are going to solve each question like hands-on. Right? So just to give you an experience on how to approach this sort of questions. So that's the goal of this lecture, right? So you are going to see all the questions from last year's exam, right? And we are going to give you a brief description on how to approach the problem and how to solve these problems. Okay. So I hope you would enjoy it. So I'll start with the data prefetching question from the last year. So you can get this question exam questions as well as the solutions from last year's website course webpage, and we are just going like using the same version here. Okay, so let's start look at the first question on the data prefetching. So you are tasked with designing the memory hierarchy of an in-order non-pipeline processor. Okay, the memory hierarchy is composed of on-chip cache and an off-chip DRAM-based main memory with an access latency of 50 cycles and 200 cycles. But consider this that this is excluding on-chip cache access latency. So 200 cycles just for accessing the DRAM respectively. In the baseline processor design, the processor first accesses the cache. If the data is not present in the cache, then the processor accesses the main memory, and assume that the data is always present in the main memory for the course of this question. Now you run an application that has the following memory request access pattern. Note that these are cache block accesses, not just the raw addresses. And assume that all the memory requests miss the cache hierarchy and go to the main memory in the baseline processor design. So how does the memory request access pattern look like? You have A plus 1, and then A plus 8, A plus 9. So you can see like these are pairs, right? So A plus 8, A plus 9, then A plus 16, A plus 17, A plus 12, A plus 25. Maybe yellow is not the best color. Okay. And then you have A plus 8 and A plus A8 and A8 and plus 1. Okay. So now also assume that the application needs to execute only the memory request and no other instructions for the course of this question. So here are the questions. So what is the total number of cycles required for the baseline processor to execute the application, and explain briefly. So always explain, give some explanation to your answer, right? So that we can also partially give you credits. If you just simply put an answer without having any explanation, that would, you know, do not encourage much confidence in us, like how exactly you ended up on that answer. Okay. So what is the total number of cycles required for the baseline processor? So the baseline processor doesn't have anything else. So let's see. So how many pairs of accesses you are seeing here? So this is one pair, this is another pair. So for n equals 0, you would anyway have one pair, right? So if n equals 1, you would have two pairs. So that means you have n plus one pair of accesses in this entire access stream that we are showing here. Okay. So now if I know that there are n plus 1 pairs of memory request addresses, so how much time each pair takes? So first memory request, as it says that the data is not present in the cache, it goes to the main memory. So how much time does it take? So if it first needs to access the cache hierarchy, so that's 50 cycles, and then it would go to the main memory. So that would take another 200 cycles. So it would take 250 cycles, right? So now if you have two pairs, one pair of accesses, so that takes 500 cycles per pair, right? So if you have n plus 1 pairs, so that means it by total it would take 500 n plus 1 cycles. Does it make sense? I hope it does. Okay. So that's the answer of the first question. So what is the total number of cycles required to the baseline processor? 500 into n plus 1 cycles. Okay. Okay. So now let's go to the second question. So the second question says, yeah, okay. To make the processor faster, you design a next block prefetcher now. For every memory access to the cache line address X, the next block prefetcher fetches the data corresponding to the address X plus 1 to the processor's on-chip cache. Assume that the prefetcher fetches the data before the application demands it. Now, what is the speed up of this new processor design over the baseline processor that you mentioned in that we designed in A? So consider this, that we are expecting the speed up value, not the absolute number of cycles, the speed up. So speed up means the speed up that you are expecting after these changes means whatever number of cycles that you have done before. So it's basically cycles before divided by cycles after. So that's the speed up, right? Okay. So now let's see, we know the cycles before was 500 into n plus 1. Fine. So now let's see what is the cycles after, right? So if you implement the next block prefetcher, what happens is that you have, let's go back to this access pattern. Yes, okay. So you have A would go to main memory, but then A plus 1 would get prefetched into the cache hierarchy. So A would take in the system with the prefetcher, A would again take 250 cycles because 50 cycles for accessing the cache, 200 cycles for accessing the main memory. So A would take 250 cycles, but then A plus 1, when you would access A plus 1 would already be prefetched into the cache. So that's the benefit of prefetcher, that next time when the processor actually demands A plus 1, it would see it only in 50 cycles because it just needs to access the cache hierarchy, not the main memory also. So for this pair, then you are going to get a cycle count of 300 cycles. Again, you have n plus 1 pairs. So that means your new cycles would be 300 into n plus 1. So that means you would have a speed up of 5 by 3. That's greater than 1. So that means you have a speed up instead of slow down. That's the benefit of prefetcher. Let's see. Okay. So now let's go to the third question. Okay. So the third question say, just give me one sec. Perfect. Okay. So now your colleague observes that accessing the cache to check whether a memory request would go to main memory also incurs a latency overhead. So he proposes an off-chip predictor that accurately predicts which memory request would go to the main memory. For those predicted requests, the processor can now directly access the main memory to get the data without even accessing the cache hierarchy first. Okay. If you implement this predictor on the baseline processor, remember this, the baseline processor does not have a prefetcher yet. So if you implement this predictor in the baseline processor mentioned in A, the first question, what would be the speed up of the new processor design over the baseline processor? Again, your speed up would be cycles before divided by cycles after. So cycles before would be 500 into n plus 1. That's we have calculated in question 1A. And then cycle after would be, let's consider what would be the cycle after. So now if you go back to this memory access pattern, right? So what off-chip predictor says that, okay, for A, it was supposed to go to the main memory. In the baseline, you would first need to access the cache hierarchy that takes 50 cycles, and then you would access the main memory, which would take.
We lost the computer. Something happened.
Okay. It doesn't sound nice. Yes. Okay, so we are having some technical difficulties. Let's see. Show the floating meeting control. Is it? It's showing over here.
Okay.
The system is working, I guess.
But the projector is not working yet, I guess. Can you check?
Maybe we can all just like watch from YouTube.
Watch from YouTube?
But can you see the doc will come from YouTube?
Yes, we can still see it.
Oh, okay, good. You're back.
Yeah. Oh, okay. Probably it somehow stopped prefetching.
Can you move your share screen thing?
So what?
The control of Zoom.
Ah, okay. Okay. This is good. Okay. Okay. Sorry for the interruption. So where were we? So we were saying that, okay, so in this case, what would happen if we have the off-chip predictor? So the first access, it would go to our main memory, but then instead of paying the entirety of 50 cycle plus 200 cycle, now you have an off-chip predictor, which says that, okay, it would predict accurately, as the question says, right? It would predict accurately that it would go to main memory. So you would directly access the main memory without even accessing the cache. So that means for the first request, you are going to just need 200 cycles. For the second request, because you are not paying the penalty of accessing the cache hierarchy, And then the second request also you would need 200 cycles. So that means for a pair, you would need 400 cycles in total. So that gives you the speed up of the new cycles after is this one. So basically it would give you a speed up of 5/4. So consider this the previous speed up. What you have seen is 5/3, and now you are seeing a speed up of 5/4. So it's lesser than what the prefetcher is providing, but it's still a speed up nonetheless because you have more than one, right? Okay. So now is this clear till now? I guess. Okay. So now let's go to the last question. So if you implement both your prefetcher and your colleague's off-chip predictor, now both of them are implemented together in the baseline processor, then what would be the speed up of the new processor design over the baseline processor design? Okay. So now we are basically combining question B, which was this one, and question C together, like the solutions together. So what would happen in this case? So consider this. What question B says that you have a prefetcher that only prefetches the second. It can prefetch the second cache block. Like seeing A, it can prefetch A+1. But then A is anyway going to main memory, right? If you have the off-chip predictor, then A is going to take 200 cycles, correct? And then if you have an off-chip predictor plus prefetcher, then A+1 is going to take how many cycles? Can anyone say? 50. Why? That's correct. So A+1 is already prefetched in cache. Have you come up to the same answer? Perfect. Okay. So that's 50 cycles. So in total, we are going to see 250 cycles. So it used to be 300 before if you do not have, like if you have only prefetcher. If you have the off-chip predictor, it used to be 400 cycles. Now, if you have both of them, it becomes 250 cycles. So now your speed up becomes 500 into n+1 divided by 250 into n+1. So that gives you 2x. So that means you have a 2x speed up. So you make the entire program twice as fast as the baseline processor. Does it make sense? Okay. So that essentially, yeah, finishes my presentation, and I'll ask the next speaker to come in.
Okay, we have the RowHammer question now. It's a short one. Let's see if I'm going to be able to finish it as fast as Rahul did. Okay. Can you hear me? Good. So this question starts with true and false questions. So let's go through them together. So we need to choose true or false for each of them, obviously. And the first one says RowHammer can be used for taking over a DRAM-based system. Is it true or false? What do you think? True? Yeah? Okay, yeah, that's true. It's shown many times. The second one says DDR3 DRAM chips exhibit vulnerability to RowHammer, but DDR4 and DDR5 DRAM chips are not vulnerable to RowHammer. What do you think? True or false? Yes, false is the correct answer. In fact, we can see bit flips in circuit level for DDR4 chips. And there are also system level exploits. And you can refer to Kaveh-Rezavi's papers, right? So it's repeatedly shown again. Okay, mobile devices are RowHammer safe because they use low power memory chips. What do you think? False? Yeah, that's true. I mean, that's false, yes. So actually, you can see low power memory chips being characterized in a paper in 2020 that we covered in the lectures. They show that in LPDDR4 chips, you have great vulnerability. Okay, the fourth one is about blockhammer. Blockhammer prevents RowHammer bit flips by refreshing potential victim rows. What do you think? How does it do that? Do you remember? Yeah.
And one prevents the frequent activation of the row, and the other throttles the application.
Yes. Exactly. The key point is it does the security with throttling, right? Not by refreshing potential victim rows. So the answer should be false. And there is no attack in the literature that defeats the RowHammer defenses which adopt security by obscurity approach. Do you remember security by obscurity approach from our lecture? If you remember, I was talking about this on DRAM die target row refresh mechanisms that the DRAM manufacturers advertise these as like RowHammer safe chips. But it turns out that they can be actually defeated, and there are a lot of reliable workarounds around them. And you can refer to trespass paper, UTRR paper, blacksmith, all of them. So the answer should be false. Okay, let's go to the second question. So this is a basic calculation. So here we have a system defined. So in our system, we have one channel, one rank, 16 banks, and each row contains 8 kilobytes of data. And the chip capacity is, or the module capacity is 8 gigabytes. Okay, so this is a pretty common system actually. So each DRAM row should be refreshed every 64 milliseconds. And there should be at least 64 nanosecond time between two back-to-back activations targeting the same bank. So you send, basically, if this is time, you send an activation here. This is time t. You cannot send another activation before t plus 64 milliseconds. Sorry, 64 nanoseconds, right? And you need to refresh each row every 64 milliseconds. So it says that we characterize this chip's vulnerability level, let's say, and we figured out that we're safe if the aggressor row's activation count does not reach to 1,000 times without neighboring rows. If it reaches to 1,000 times, then we have bit flips. So now in this question, we are in the attacker's situation, attacker's point, and our goal is to hammer as many rows as possible and induce bit flips on all of them. So what should we do? We should, we have a budget of activations in a 64 millisecond time window, because after 64 milliseconds, everything will be refreshed. And we need to hammer as many rows as possible. So between two activations, we have to wait for 64 nanoseconds. So 64 milliseconds over 64 nanoseconds is around, actually exactly here, 1 million activations, right? We have the budget of 1 million activations. We can distribute these 1 million activations to different rows. And the question is asking like how many rows in maximum we can do that. So each row needs to be activated 1,000 times. So if you divide this by 1,000, you will see that we can hammer 1,000 rows concurrently. So this is a huge attack, right? So this is the question. Okay. In the second part of this question, now we have a RowHammer mitigation mechanism. This mechanism was quite new actually at that time. This exam is from 2022, and this paper was also published in 2022. So we did not cover this paper in the lecture, but actually all the explanation is here. So what this paper does is it proposes a RowHammer defense mechanism, and in this defense mechanism, it remaps an aggressor row when an attack is detected. And how does it do that? It does it in these 4 steps. So let's say row A is being hammered, and it detects it. What it does is it fetches row A's content into the row buffer, into the buffer in the memory controller, and also fetches the content of row B. Oh, sorry. Yeah. Okay, I'm talking about these 4 steps here. So it first fetches the row A's content into a buffer in the memory controller, and then fetches row B's content into the buffer in memory controller, and then writes row A's content to row B and row B's content to row A, so that you swap the rows and you change the mapping. And let's say the attacker keeps hammering this row, row A, let's say. After this operation, it will hammer row B, so that you will not accumulate too many hammers on row A to induce bit flips. So this is what this mechanism is doing. And we are trying to evaluate the worst case data movement overhead of this mechanism. So now in this case, our RowHammer threshold is 1000. So we will perform this operation every time a row is activated 1000 times. And DRAM channel bandwidth is 20 gigabytes per second. And the question is asking for the worst case data movement overhead. And there's a hint here that actually tells you like how to do this calculation step by step. So first, okay, calculate number of bytes that need to be moved between the memory controller and DRAM chip in 64 millisecond time window, right? So we already know that we can perform this operation 1000 times, right? Because RowHammer threshold is 1000. And from the previous part of the question, we already know that, or you can also calculate in this question, it's not dependent. In 64 millisecond, oh, it's dependent actually, but it's an easy calculation. In 64 millisecond, you can perform 1 million activations. So 1 million over 1000 is 1000. So I can trigger this operation 1000 times in a 64 millisecond window. And we know that the row size is 8 kilobytes. So we fetch this row. So we move 8 kilobytes from row A to memory controller, another 8 kilobytes from row B to memory controller. And then we move these two 8 kilobytes back. So in total, we end up moving 32 kilobytes. If you consider like back and forth, right? In one operation. And I can perform this operation 1000 times. So I can basically around 32 megabytes, right? Let me double check with the numbers in case I do some miscalculation. Yes. So every operation takes 32 kilobytes, right? So let's not get into this. I missed actually one point here while solving. Please be careful and don't miss it. So in this system, from the definition in the first part, we know that there are 16 banks, right? And I can also perform this attack in parallel across all banks. So actually, I can trigger this operation 1000 times in a single bank and 16,000 times in the whole rank, in the whole DRAM module. And all the banks are sharing the same channel, right? So whatever operation I do for whatever bank, it will be consuming the memory bandwidth. So I perform this operation 16,000 times, and every time I move 32 kilobytes of data. And if you calculate this actually, it goes to somewhere around 500 megabytes in a 64 millisecond time window. And we can calculate how much time does it take to move this 500 megabytes on this bus by using this memory bandwidth. And we also have a simplification here for easy calculation. So you can see that it's actually taking around like 25 milliseconds to perform this operation. And this happens in 64 milliseconds, right? So you have 64 millisecond time window, and you have 25 milliseconds of this time window for just for RowHammer mitigation mechanisms. And if you calculate this ratio, it's around like 39% of the available memory bandwidth is gone because of this RowHammer defense mechanism. So, sorry.
Here we consider that each attacker row has only one victim row, but shouldn't it be possible to have two victim rows, the two neighbors? So we should transfer so A and B, and then A1 and B1, so double the transfer.
Yeah, so that's correct. It can happen in that way as well. But here in this question, actually, even if you calculate in that way, you will reach the same conclusion because it's about the activation budget you have in that limited time window. So you can dedicate some of that budget to some rows and some of them to some other rows. Or you can put all activations on a single row. So here, the RowHammer defense mechanism already like guarantees that there is no bit flip. But like every 1,000 activations will trigger this kind of operation. So you're right that it doesn't have to be like particularly row A and B for every single, yeah. This row A and B does not necessarily need to be the same row A and B for all operations here. So it can be from like different rows. Yeah.
What I was saying that like say X is the attacker row, and
Yeah.
so the victim are X minus 1 and X plus 1.
Yes.
So I need to swap both X minus 1 with another and X plus 1 with another.
Okay. So I understand the confusion. So it happened because I didn't read the whole question actually here. If you read, you will see that this mechanism is actually an aggressor-based mechanism. So it only moves the aggressor row, not the victim rows. Yeah.
I have a question about the fact that you can do the attack on the 16 banks in parallel, because so from my understanding, if you can only send the activations every 64 nanoseconds, it's to one specific row, like you can't send to all 16 rows at the same time.
Yeah, so the assumption is that here. So that 64 nanosecond is for targeting the same bank. But if you like, you send an activation to bank 0, and then you send another activation to bank 1, you don't have that restriction over there. Yes. So in real systems, it's not like that independent. There are some other time constraints that avoid that. But it's not in the scope of this question. It's quite simplified here. Other questions? No? Okay. So the last part of the question is quite straightforward, actually. It asks you to list one advantage and one disadvantage for each of para and block hammer mechanisms. We already like presented all of these works in the class. So para is the one that was published in ISCA 14, and it's basically the probabilistic mechanism that does not store any memory. Whenever you see an activation, you flip a coin, and with some low probability, you perform victim row refreshes or not. And in block hammer, if you remember, we have a bunch of counting balloon filters, and we keep count of the activations, and then at the end we decide like if we should blacklist some rows or not, and then when we blacklist some row, then we were throttling the accesses to that row. So from the papers themselves, actually, you can also see that, and you can come up with like any advantage, disadvantage, as long as like for this kind of open-ended question, if what you say makes sense, you will get the points. It doesn't have to be like exactly what I put there, but I put here, maybe I can just show this here instead of writing. Just like two simple advantages and disadvantages. So para is advantages because it has low hardware complexity. You don't need to keep track of some complicated data structure. So it has almost zero area overhead. And the disadvantage is it can cause large performance overhead because it's oblivious to the memory access pattern. And on the other hand, block hammer can give you low performance overhead because it does not throttle all accesses. It selectively throttles the accesses that are identified as the aggressor rows, that are targeting the aggressor rows. And the disadvantage is the high hardware complexity because you need to implement a lot of counters. So if you have some other advantages, disadvantages in your mind, please share. Sure.
Another disadvantage of para is the fact that physically adjacent rows may not be the logical adjacent rows.
Yeah, exactly. So block hammer solves that problem, right? It's one of the motivations, but it's still a problem for para because it doesn't know the like what row is physically adjacent to what row. Perfect point. Yeah. Any other? Okay. So that's the end of the question. Thank you very much.
So I'm going to solve the PIM question. Easiest question in the exam. So usually you're going to see that's a lot of text in the PIM questions, but if you know the background, you can skip them. But basically here is describing Ambit. I present Ambit during the lecture, and is explaining that you can do bitwise and or operations in Ambit. And to do that, you use a vertical data layout where you place different bits from an input element, from a scalar element across a single DRAM column. So here you can see bits, there are 4 bits, 0 bits, 0, 1, 2, and 2, 3 are placed in a single DRAM column. And by doing that, you can enable arithmetic operations. You can do addition, multiplication, division, subtraction. And in this particular question here, is asking you to do subtraction. And there is a prior question similar to this one that is actually asking you to do addition. I guess it was in the homework. So it's similar to that one, if you are familiar with that question. And here is telling you about the system that you're going to use for this question. You're going to compare 2 systems, a CPU-based implementation that reads elements from array A and B from memory, subtracts them, and writes the result back onto array C. And also it's telling you for you to figure out the performance of the CPU-based implementation. You use 2 micro benchmarks. Oh, that is later on actually. But by saying that you use analytical model where the time of the computation of the CPU is basically the number of operations that you're going to do times a constant plus the time that it takes to read data from the DRAM. So the number of bytes that it reads divided by the DRAM bandwidth. And here we have also the Ambit implementation, which is going to use the bit serial design to implement the subtraction using only XOR and NOR and OR operations, as you see in figure 2. Okay. So this first question, first part is just introducing the question. There is another page just introducing the question. So this is the circuit for the subtractor that you're going to implement. So you have some XORs, some AND, OR, some NOT, some AND, and some XORs. And here is telling you that Ambit implement those operations by issuing activate pre-chart commands. So by simultaneously activating several rows together. So it says here, AAP XY represents double row activation of row X and Y, followed by a pre-charge, and AAP represents triple row activations of row Z, Y, X, Y, and Z, followed by a pre-charge. If you are familiar with the Ambit paper, you're going to see that this is a bit different from what is in the paper itself. In the paper, this triple row activation is a single AP because there is a special row decoder that activates the 3 rows at the same time. But basically, it's the same idea here. It's just that we are sending the 3 activations one after the other. And here there is a table that shows how Ambit implements AND, OR, and XOR. Note there is no NOT, it's just OR, AND, OR, and XOR. In those instructions, Ambit copied rows D, Y, and DJ to auxiliary rows. The control rows dictated if it's an AND or an OR operation. DRAM rows with dual contact cells are used to perform NOT operation and basically explain how it's done. And then there are some information here about the DRAM system that you're going to use during this question. So the DRAM row size is 8 kilobytes. Activate commands takes 40 nanoseconds, pre-charge 20. The DRAM has a single bank. The syntax of Ambit operation is BBOP and or XOR. Destination source 1, source 2. The rows at addresses 5, 6, 7, 8, 9 are stored partial results. They all contain zeros initially. The rows at address A, B, C stores array A, B, and C. And the row at addresses D and E store pre-initialized values containing all ones and all zeros, respectively. So this is with 1, this is with 0. They are all byte aligned. and everything belongs to the same DRAM row. So after reading these 2 pages of question, you can start doing the question actually. Okay, so in the first part, you're going to figure out the time that it takes to execute the computation in the CPU. So for the CPU-based implementation, you want to obtain K and M. To the end, you run 2 experiments. The first experiments, you run CPU code for the element-wise array subtraction for 65,000 32-bit elements and measures that TCPU is that one over there. Is microseconds for you run a code for the subtraction. In the second experiment, you run a stream copy benchmark. So stream copy benchmark basically copies one array to another array. There is no computation, it's just the copy. It's actually explained here. And then you measure that the TCPU for a string copy was 10 microseconds. String copy. And then ask you to figure out what are the values of K and M. So recall here, this is the equation that we're going to be using. So the time CPU is equals to K times num operations plus num bytes divided by M. So the easiest way to figure out this is first calculating the value of M based on the stream copy, because as the question tells you, stream copy does not do any operations, it's just a copy, right? So this first portion here, K times num operations is 0. So you know that the 10 microseconds should be equals to the number of bytes that you're going to read. So you're reading 128 32-bit elements. So both input and output, right? So this is going to be 2 times that. And each one is 32 bits, so 4 bytes. Divide by M. And I'm not going to do the math here. You're going to find a number. Important thing, especially in the PIN question, you might have some annoying math to do. Don't do it. If you simply isolate M here and put in terms of the other things, I'm going to grade you with 100 of the total points. If you try to do the math and you make a math mistake and I figure out, I'm going to remove points. So don't try because the exam is quite long and it's not worth it. But then I already have the calculations done here because I don't want to remove my own points. So this is going to give you that this number here. Is there any question how this was done? Okay. Okay. Now you need to figure out the value of K. So you use the same thing. You're going to use the second benchmark suite that we was used. So this is 100 microseconds here. This is going to be K times the number of operations that was done. So you did 65,536 additions, subtractions, right? So this is 65,536 times the number of bytes that was read from the memory. So now you have 3 arrays, right? So you have 3 arrays, and you read 65,000. 65,536. Each array is 4 bytes. And the throughput is 102 gigabytes per second. And then if you isolate K here, you're going to find 1.4 nanoseconds per operation. Again, if you just write this equation here in the exam and isolate K, but don't do any math, you can leave this 3 times, blah, 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 is all good. You don't need to finish the math. just isolate the parameter that the question is asking for. That's enough. Is there any questions here? Okay. Now the second part. Write the code for the Ambit-based implementation of the n-bit element-wise subtraction of arrays A, B, using BBOP and or and XOR instructions. The result array is C. Show your work. Okay. So basically, the question is asking you to translate this figure here into BBOPs. And it already gave you a bunch of register elements here, right? So you know that this element here, I'm going to use another color so do not get confused. So you know that this here is array A. You know this is array B. Why do I know this? Because it was written there, right? Yes, this here. So this is A, this is B. C thing is a temporary thing, so I'm going to call this temp1. This is temp1 again, right? This is another temp2. This is C is the output, right? C. D, what is D? D is a row initialized with ones. So I have 1 here. And A here is A, right? And then B is B. And then I have 0, 8, which is another temp. I'm going to call this temp3. This is another temp. I'm going to call this temp1 because I already called temp1. And D was 1 again. And then 0, 8 was another temp. Which temp I lost? Temp 3. Oh, there was more temps here. So this is actually 0, 8 is another temporary value. So 1, 2, 3. This is going to be 3. Now it's good because it's also 3, 3. This is going to be 4. 1, temp 1. This is temp 3. This is temp 3. This is 07. Did I use it before? Yes, temp 2. This is temp 1. This is, I think I used this guy, temp 4. And this is temp 1. And this is temp what? Temp 2. Okay. So this is already mapped, so you need to map the operations accordingly, right? Because the inputs are already set for you. So now you look here, and then you need to figure out if you're going to use a AND operation, not AND. What were the operations? Or XOR. Okay, so here we have A and B, and giving output. So this is the first this XOR node here, right? A B giving output. So this is the output here is going to be temp 1. And this is a XOR. So you just need to put here XOR. And then this is temp 1, which I wrote here, with temp 2. Temp 2, you can consider that is the carry in here. So this is another XOR. I'm going to look at the solution so I don't make a mistake. Yes. Okay, this is the initial carry. You can consider that is in a temporary register. XOR. This is 1 and A, generating temp 3. So you need to implement some NOT operations, right? But there is no NOT. I didn't give you a BBOP NOT to operate, giving a NOT operation. So you need to figure out a way of doing NOT with AND or XOR. So if you look at the truth table, of a XOR, if I call this A, you're going to see that if I set one input to 1, and the other input of the XOR to my input, I'm going to have the negated value, and I highlighted the wrong place here, is here. This one and this one. And one here, one here. You're going to see the output is the negated value of A. So this is the trick of this question, is to figure out that you can do XOR using, you can do not using XOR. So you're going to continue translated. So now you know that this XOR here is going to become XOR. This is going to become XOR. There is only these two actually. So this is one with A and a temporary. So this is definitely A here. This is definitely this guy here, right? And this is storing temp3. This is XOR. Then you have temp3 and B. So B here and temp3 is this AND gate here, right? So this is AND. This is temp4. Then you have one with temp1. So this is temp1. Oops, sorry. This is temp1, and there is a 1. So this is definitely this NOT gate here, NOT gate, generating temp3. So this is a XOR. This is, then you have temp3, this guy, and temp2, which again is this carrying that is coming here. And then this is an AND. And then in the end, you have, you're just missing this guy here, right? Temp1 and temp4. I stored this in temp, this I call it temp1 now. Temp1, temp4, this is a OR. Okay. So then you have the equation. Don't forget that there is this box here. So this is bit 0 computation. So this needs to repeat n times. Is there a question how this is done?
Why don't we use the I actually? Because there it seems that it does n times the same computation.
I didn't understand the question. Can you repeat, please?
Why is the I not used in this loop?
The I is not used. What I? Just the. It's because, so this is repeating any times. So the way that this is implemented in hardware later on is that the I, there is an internal counter there that is counting for this I and figuring out the offsets. So the question does not ask you to figure out that, but if you go back to actually the Simduran paper that I presented some time ago, I explained over there that there is a control unit that translates these BBOP instructions into proper activations, and over there the I is a parameter, but it's transparent from the user, so you don't need to worry about it. Okay, is there other question how this is done? Okay. A lot of fun. There is also. So here it's just explaining you to, if you have some, if you did some assumptions for you to write it down. So here would be good to write down like, assuming that not is equivalent to, equivalent symbol is this one actually. XOR 1A, blah, 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 blah. But you don't need to write much. It's just for me to understand what you did. A lot of people last year put a not here, and then would be wrong because I didn't give you a not. Okay. Compute the maximum throughput in terms of arithmetic operations per second of the Ambit implementation as a function of the element size n, bits per element. To simplify your calculation, you can assume 8 kilobytes, 65,000. So throughput is always the number of operations that you do divided by time. So the number of operations that you're going to do is fixed, right? Is the number of rows, is the number of columns that you have in a row. This is 65,536. And now you need to figure out the time this is going to take. So the time that is going to take is quite straightforward. You go here, you have to implement 1, 2, 3, 4. So you have to do 4 the time of or XOR plus. Why did I put 5 there? It's 4. Plus 2 ORs plus 1 AND. And then you go here to this table, and then you count the number of activations that each one of them do, like AND does. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 activations. And 1, 2, 3, 4, 5. 5 pre-charts. And then you go back to the question, and then you have the latency for the activations in the pre-charts. And this is 12 times 40 plus 520 times 20. And then you do the same for the other ones. It's a bit boring. But I'm going to see the result here because it's just counting. This is going to give 6,000 times n. Don't forget the n because it's asking as a function of n. Nanoseconds. So basically, you come here, then you put this 65,536 divided by this. Times n. And this is nanoseconds. Again, if you just write the time with the equations and you leave like 12 times 40 plus 5 blah, 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 times blah, 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 and then you place it back here in the equation, is great. I actually prefer that. Doing grading is much easier. But if you do the math and then you do it wrong, then I don't know what you did, and then I'm going to think it's wrong, and then I'm going to remove points. So is there any question how this is done? Okay. So then the last part is asking you what size of elements the CPU implementation is faster than the Ambit implementation. Okay. So for you to figure out this, we need to find that you want that the time of Ambit be larger than the time of the CPU. We already have the time of Ambit from the previous question, right? So this is 5,500 times n times. So this is just because I'm converting from nanoseconds to seconds. And the time of the CPU, you figure out the k and m values earlier, right? So this is 1.4 times 65,536 times 10 to the minus 9 plus 65,536 times 3 times n divided by 8 times 4 time. This 10 and 10 to the 9s are appearing here just because I'm converting back to nanoseconds to seconds. Don't need to do that actually. And then you isolate n, and then you find that n is going to be larger than 14 bits. Again, write the equation, do a little bit of math to isolate n, and write as a function of the equation. Don't solve the fractions. And then you're done. And I guess it's pretty much that. Is there any question? I guess not. So for the pin question, it's a lot of text, but it's not particularly hard to solve. You just need to pay attention to the details.
Hello, everyone. Let's solve this DRAM refresh question. Let's read the question first. So, we have 4 channels, 1 rank per channel, 8 chips per rank, 16 banks per chip, and 2 to the power of 17 rows per bank. The refresh interval, REFI, which is how often the memory controller sends a refresh command, is 3.9 microseconds. And the refresh window, or how often every DRAM row is refreshed, is 32 milliseconds. A refresh command refreshes a certain number of rows, assuming a power of 2, in all banks of a rank. It occupies the command, so every refresh command occupies the command bus for 1 nanosecond, and the DRAM device spent 600 nanoseconds refreshing the rows for every refresh command. So the first question is asking how many DRAM rows in a bank are refreshed for a refresh command. So because we know that every row will have to be refreshed every 32 millisecond, and like a refresh command will be sent every 3.9 microsecond. So the number of refresh commands is just 3.9 microsecond over 32 millisecond, which is 8K refresh commands. And these 8K refresh commands will refresh 2 to the power of 17 rows per bank. So the answer would just be 2 to the power of 17 over 8K. So we have 16 rows. So then the second question, what are the refresh commands command bus occupancy? So that is the fraction of the time that the command bus is occupied by the refresh command. So we have, so within a refresh window, which is 32 millisecond, we have 8K refresh commands. So that's like 8K commands times 1 nanosecond over 32 millisecond. That's the command bus occupancy, and the answer would be 0.0256%. And as a reminder, in the actual final exam, you do not have to evaluate these equations as long as like you have the proper units and your intention is clear. We will give you full points without a final numerical answer. And second, the bank occupancy, which is the fraction of the time that the bank is busy serving refresh commands. So the with like the same formula, because now we are computing the time that the DRAM device is spent refreshing, so it takes 600 nanoseconds instead of 1 nanosecond. So the answer would be 15.36%. Okay, so by far, is there any question? Oops. Yeah. Okay, so then let's move on to the next part. So now the DRAM engineering team claims that they can retain data for 128 milliseconds instead of 32. So that means so every row will only have to be refreshed once for every 128 milliseconds. However, upon further testing, we find that this DRAM technology is very susceptible to variable retention time, VRT. So if the DRAM cell is a VRT cell, then it can experience 2 leakage state. A high leakage state where it only retains data for 16 milliseconds, and a low leakage state that it can retain data for 128 milliseconds. And the normal DRAM cell can always retain data for 128 milliseconds. So the question is asking, assume we have a smart memory controller that knows the distribution of the VRT cells in the DRAM device. Then this memory controller can send refresh commands at different rates to the DRAM rows that contains VRT cells and does not contain a VRT cell. So it's asking what is the minimum number of DRAM rows without any VRT cells, so such that the bank occupancy of refresh operation of the new DRAM device is no longer than the existing DRAM, which we have just computed here. Yeah, assume the same DRAM organization, the same TRFC, and the DRAM and the refresh common refresh is the same number of DRAM rows as in question A and B. So let's say the old occupancy is 8K times 600 over 32 millisecond equal 15.3 36%. Is this correct? Yes, this is correct. So yeah, now with this new intelligent memory controller, basically we can send refresh commands to part of the DRAM rows with less frequency. So yeah, because a normal cell can retain data for 128 millisecond all the time. So the let's just consider 128 millisecond refresh window, and let's say X refresh commands are sent to the VRT to the DRAM rows with VRT cells that could be in the 16 millisecond refresh window. Then the bank occupancy would be since it's asking without any VRT cells, so let's just set X to let's say the DRAM command, the DRAM refresh commands to non-VRT rows. So in a 128 millisecond refresh window, we will have X times 600 nanosecond. This is the time that the DRAM bank spent on refreshing the non-VRT DRAM rows, and 8K minus X, which is the refresh commands to the VRT to the DRAM rows with VRT cells, and they will have to be refreshed 6 nanosecond over 6. Oops. It's 128 millisecond over 16 millisecond, because they have to be refreshed that many often, and also times 600 nanosecond over 128 millisecond. And if we solve for X, yeah, and this should be smaller than 15.36%. Yeah. If we solve for this, then we have X should be larger or equal than 4,682. This many DRAM refresh commands that goes to the non-VRT DRAM rows. And because one refresh command refreshes 16 DRAM rows, then we know that at least 74,912 DRAM rows must be without VRT cells. Yeah, I hope this is clear. So next. Yeah, so the engineering team reports that it could not guarantee that many VRT cell-free DRAM rows in a bank, as we have calculated in the previous question. So we have to look into the workloads memory access pattern to find appropriate, to find opportunities to reduce the refresh cost. So luckily, the data center dedicated to run a particular workload with very regular access pattern. So for simplicity, we consider a single VRT cell located in a row A. So the workload accesses row A exactly every 64 milliseconds as at timestamp T1 and T3. And the system is configured such that row A is refreshed every 64 milliseconds at timestamp T0 and T2. Refresh are not synchronized with workload accesses. This means that T2 can happen at any time between T1 and T3 with equal probability. And the cell will change its leakage state with a 30% of probability when the word line of row A is enabled. So this is important because it says as long as word line of row A is enabled, so both activation and refresh can change the leakage state. And initially the cell is in a low leakage state and it will get refreshed immediately at timestamp T0. So we need to calculate the probability of not violating the retention time of the cell for 64 milliseconds of execution given these configurations. And it also provides a hint that we can construct a like a state transition probability tree to basically to evaluate all the possible outcomes, and then we can compute the probability. So as said in the question, the cell is initially at a low leakage state. So at T0, when it's refreshed, because we mentioned as long as the word line of row A is enabled, it will change the leakage state with a probability. So at T0, we immediately have two possible outcomes. Let's say, yeah, at since it says like the state will change at the 30% of probability, so it has a 30 so like 0.3% of going to the high leakage state, and also 0.7% sorry, also 70% chance of staying in the low leakage state. Then similarly, let's use AL and H to denote the low and high leakage state at T1 when the row is accessed by the workload. We also have at least 4 outcomes, and the chance of staying is still 0.7, changing is 0.3, staying, changing 0.7, staying 0.3. So because the question is asking the probability of no retention time violation at T2, so we just have to evaluate the chance of each of these 4 cases and see which of these corresponds to no retention failure, and then we get the answer. So first, let's examine the leftmost L state. So since both at all times it stays in low leakage state, so it means it can retain data for 128 milliseconds. And we know that like the time between T0 and T2 is just 64. So there could not be any retention time violations. So this is a go. And this is like 0.7 times 0.7, 0.49 chance. And for this H state, initially it's in low and then in low, and but after the axis of T1, it will change to a high retention state. So this means that okay, so okay, wait a second, let me. Yeah. So since after T1, the cell is in a high leakage state, this means that if we would like no retention failure to happen at T2, then the interval between T1 and T2 should be less than 16 milliseconds, because in the high leakage state, the cell can only retain data for 16 millisecond. And we also know that between T0 and T2, it's 64 millisecond. Since like this is should be less than 16, then we should have like the interval between T0 and T1, let's call it TD. So TD should be larger than 48 milliseconds, so that T2 can happen at most 16 milliseconds after T1. So the probability of this is 0.7 times 0.3 times the probability of I say TD larger equal than 48 millisecond. And then for the third L case, because after T0, it's already in a high leakage state. So in order to prevent retention failure, this this interval TD should already be smaller than 16 millisecond. Yes, and then for this final H state, so both are in the high leakage state. So yeah, then this cell can only retain data for 16 millisecond, and there's no chance like these two intervals can extend to 64 millisecond. So yeah, then in this case, no matter what, there will be a retention failure. So yeah, this is impossible. Then the final probability is just the sum of these three. Yeah. Yeah, sure.
For the bottom right of the tree, Isn't it reverse the probabilities, like from high to high it should be 0.7? I guess maybe it doesn't matter in the answer, but
So it says like if the state is changed, then it has a 30% probability. So from low to low, it's 70%. Low to high is 30%. High to low, it's yes. So yes, this should be 3 and 7. Yes, and this should be 3. Yeah. Thanks. Okay, so if there's no further question, I think that's all for this DRAM refresh question.
Genome analysis. So we expect kind of a high-level understanding of these genome analysis workloads. So I guess as Geraldo mentioned for the PIM question earlier, if you remember that background, you can save a lot of the reading effort here. So basically you're asked to evaluate multiple ways of doing read mapping. So you're given a reference genome, reads, and you know how large they are. So you know the reference genome is like 3 times 10 to the 9. Wow, that was a bad color choice. 3 times 10 to the 9 characters, so 3 billion, yeah? Maybe I can write it down again. 3 times 10 to the 9. There we go. Now it's visible again. So, you know the size of each read, you know the size of the reference genome, and now you're evaluating multiple ways of doing read mapping. First one is the naive strategy here. So you're given simply a dynamic programming algorithm that can do full computation by computing n times m cells. So for 10 to the 6 reads, over here, and for 10 to the 6 reads, that's simply multiplication 3 times to the 9 times 10 to the 3. So that's your dynamic, the size of your dynamic programming table that you're computing, times the number of reads you have, 10 to the 6. And that's in total what? 3 times 10 to the 18. That's the number of dynamic programming cells with the naive strategy. All right, so that's obviously what we're not doing, but you're supposed to evaluate it as a baseline and get familiar with the way that you should calculate in this question. So next, you're evaluating the seed and extend strategy. So again, if you remember how this roughly works, you can save a bunch of time in reading here. But essentially, you do seeding instead of comparing the full to the full reference. Every time you just get a bunch of candidate locations for each read, namely 100 of them. So each read has 100 candidate locations. Then when you have those 100 candidate locations, you evaluate each of them by computing n square dynamic programming cells. N is still the read length. So calculate to evaluate a single location, do 10 to the 3 squared, 10 to the 6 cells candidate. Right? And then each read has 100 candidates, so it's 10 to the 6 reads times 100 candidates times 10 to the 6 cells per candidate. That's in total 10, 14 cells. Okay, so we're approaching like a reasonable strategy here from 10 to the 18 to 14. Now we're looking at the smartest approach, that's seed filter extend. And you're giving a filtering algorithm that runs between seeding and this extension thing that requires dynamic programming. And your filter can filter out 72% of candidate locations. So yeah, go ahead. Thank you. There we go. So if the filter removes 72% of candidate locations for each read, that means out of the 100 we had before, now we only have 72 candidates for each read. But the same logic, then the calculation remains 10 to the 6 times 28 times the 6. That's 2.8 times 10 to the 13. Okay, so 28 here is not filtered. Because the 72% are filtered. Makes sense. Okay, so that's the dynamic programming part of seed filter extend. Now you're also supposed to calculate the number of operations that are required for filtering. So we're giving another number here. It's 0.1 times n square operations to evaluate a candidate location with a filter. Yeah, that's not dynamic programming cells, but we call them filtering operations here. Still for the same 10 to the 6 reads. So it's 10 to the 6 reads times 100. Note it's, oh, I'm using so much space. Right. So it's 10 to the 6 reads still. Now we have 100 candidate locations again, not 28, because the filter needs to evaluate all of them. Right? Filter is supposed to reduce the number for alignment, but the filter has to do all of them. Then each of those candidate locations is 10 to the 3 squared times 0.1. That sums up to 10 to the 6, 10 to the 8, 10 to the 14, 10 to the 13. Managed to consistently write outside the box. Thinking outside the box. Okay, I hope that makes sense so far. Let me know if there are any questions up to here. So that was kind of the baseline calculation for the follow-up questions now. We're going to bring in a concrete hardware now that calculates these 3 schemas. Namely, first we have just a regular CPU. So just a regular CPU, it runs at 1 gigahertz, and it's kind of an idealized CPU. Okay, so it uses only a single clock cycle to calculate a dynamic programming cell or perform a filtering operation. So runs at 1 gigahertz, 1 cycle latency. That's to simplify the calculations. So what you simply do is you're supposed to calculate how long this takes in CPU seconds now. And you simply take these numbers. So for example, before you had 3 times 10 to the 18 dynamic programming cells to calculate. Yeah. So if your CPU runs at 1 gigahertz, that means it can do 10 to the 9 operations per second. So for the naive strategy, it's 3 times 10 to the 18 divided by 10 to the 9. Gives you 3 times 10 to the 9 seconds. So same thing for the seed and extend. Abbreviate SE here. So we had 10 to the 14 divided by the 9, 5 seconds. Then for seed filter extend, it gets slightly more complicated because we have to account for both let's see, we get a move on screen. There we go. So we have both the dynamic programming calculation plus the filtering operations down here. So what you have to do is 2.8 times 10 to the 13 plus 10 to the 13 divided by 10 to the 9. That's 3.8 times 10 to the 4 seconds. Right. By the way, on the master solution, we calculated this down to actual like human readable wall clock time also. You don't have to do this because you're asked for CPU seconds, but it's 95 years, 27 hours, and 10.5 hours. So better algorithms are great. Okay, so that's the, let's say, wall clock time on a simple CPU. Now you're given an accelerator for the same task. You're supposed to choose which is fastest. So naive, seed and extend, or seed filter extend, in the presence of an accelerator with a CPU. And you need to argue why that's the case. So your accelerator can calculate 10 dynamic programming cells per cycle. The CPU could calculate either dynamic programming cells or the pre-alignment filtering algorithm. Note that the accelerator cannot execute the the pre-alignment filtering algorithm. So the CPU has to execute filtering on its own. The dynamic programming can be done by both. So in the case of naive, we simply kind of get an 11x acceleration. Yeah, so y11x, so we have somehow the throughput of 1 cell per second by the CPU, and then we have 10 cells per second by the accelerator. So that means if we take the number from up here, yeah, the same number, like 3 to the times 10 to the 9 divided by 11. Okay, that's for naive. And seed and extend also just gets accelerated. So 10 to 5 divided by 11. So clearly, naive will never be quickest. Definitely seed and extend is faster because it's simply less work done with equal throughput. And the question now is, which is faster, seed and extend or seed filter extend?
Very short question.
Yes.
Why are you dividing by 11, not 10?
Yeah. So you have a CPU that can calculate 1 cell per second, and you have an accelerator that can do 10. And maybe I should have said that here explicitly, yeah. So they can run in parallel, yeah. Kind of collaborate. Question. So the seed filter extend thing, as I mentioned, the accelerator cannot help with the filter operations. And as it turns out, actually, the filtering operations themselves are just slower on the CPU than if we did seed and extend with the accelerator. So there are 10 to the, if you believe me that, there are 10 to the 13 filtering operations that we calculated before down here. So or the SFE, that's at least, right? You have other runtime also for doing the dynamic programming, but for the filtering alone, it's 10 to the 13 divided by 10 to the 9 seconds. That's 4 seconds already, which is already more than over here. Yeah, 10 to the 4 is more than 10 to the 5 divided by 11. You would need to do some calculation like that and write one nice sentence explaining what the hell you just wrote down. But the answer is B, okay? Seed and extend is fastest, because they can collaborate nicely somehow. Was that too quick? Did that make sense? Okay. So if you were following those those explanations in F, then G should be a really simple one. That's why there's also much less space to answer. Namely, now all of a sudden your hardware accelerator can also execute the filtering instructions. So it can do either dynamic programming or filtering, just like the CPU. And in the presence of that, simply, of course, seed filter extend is fastest, because similar to how, I see I should put this up again. So similar to how up here, seed and extend is simply faster than naive because you have less work at the same throughput. Now all of a sudden down here, you also have less work overall at the same throughput. Seed filter extend, and that's it. If you're familiar with these, rough read mapping, high-level understanding of how the read mapping works, this can be very easy and quick points in the exam. I don't think you need to understand too in-depth the entire genomic stuff for the sake of the exam. Questions?
Yes. In F, the seed filtering extend.
How does the new calculation about the prefiltering extend work exactly?
Yeah. So I didn't do the full calculation. Okay, I did some abbreviated version because the question is just which is fastest. And all I did is I showed it's slower. And how I did that is I just showed that filtering alone, yeah, the F in seed filter extend, which can only, let's see, only the CPU can do the filtering. Yeah, this F. So I'm saying if only the CPU can do filtering, we're getting the number of filtering operations divided by the CPU throughput. And just that part of the work alone is already slower than doing the full seed and extend with the help of the accelerator. Is that good? But otherwise, yeah, you could, of course, calculate the full runtime if you wanted to. All right.
So this question is about memory quality of service. Let's start. So in the lectures, we introduced a variety of ways to tackle memory interference. And in this problem, we'll examine the blacklisting memory scheduler, BLIS. And there are two key aspects of BLIS that you need to know. When the memory controller services n consecutive requests from a particular application, this application is blacklisted. And this non-negative integer is called the blacklisting threshold. And the blacklist is cleared periodically after 10,000 cycles. So every time we reach this epoch of 10,000 cycles, we clear the blacklist. There's no blacklisting anymore. And to reduce unfairness, memory requests in BLIS are prioritized in the following order. First, we service the non-blacklisted application requests. Next, we service the raw buffer hit requests. And then next, the older requests. So let's see what the description says. We have a system with 2 channels and 2 banks in its channel. And tables 1 and 2 show the memory request stream in the same bank for both applications at different times t equals 0 and t equals 10. And this is the stream that you can see. And it says that for both tables, a request on the left-hand side is older than the request on the right-hand side in the same table, which means that this request is older than this request. So if this was issued, let's say at t equals 0, this was issued at t equals 1. The applications do not generate more requests than those in tables 1 and 2, and the memory requests are labeled with numbers that represent the raw position of the data within the accessed bank. And you can assume the following for all questions. A raw buffer hit takes 200 cycles, a raw buffer miss takes 400 cycles, and a raw buffer conflict takes 550 cycles. And all raw buffers are closed at equals 0. So what do we need to do if all raw buffers are closed at equals 0? We first need to activate, which means we have a miss, right? So we see these two streams. So these are the memory requests of the two applications at t equals 0. As you can see, application A has not issued any requests. It's only application B that has issued 1, 2, 3, 4, 5, 6, 8 requests. And then at t equals 10, both applications have 8 requests. And as you can observe, and as it says in the caption here, note that none of the applications B's existing requests are serviced yet. What does this mean? That all the requests of the application B are older than the requests of the application A. So in terms of age, this means that B's requests are more old than A's requests. So what's the first question? Compute the slowdown of each application using the RFCFS scheduling policy after both threads run to completion. And we define slowdown as the memory latency of the application when run together with other applications compared on top of the memory latency of the application when run alone. Do you guys remember what's FRFCFS? Does someone want to say? You can say.
First the raw hits, then the first come first served.
Correct. Okay, so when we see raw buffer hits, we might schedule from different application. And then it's who basically entered the queue first. It means in terms of age. So let's see how to solve this. So first, what did we discuss about the first request? So the first request, all the raw buffers are pre-charged, right? So to first calculate this equation that I showed you before, this one, we need to find the denominator, right? Which is the memory latency of the application when run alone. So we need to first calculate how many cycles it takes for each application to execute all the requests when run alone. So let's say that we want to execute application A alone. In this scenario, what is the first request? How many cycles will we spend for the first request? It's a raw buffer miss, for sure. Why? Because we need to activate a row, right? So and we saw that the raw buffer miss takes 400 cycles. So for sure, we need 400 cycles. And which one did we activate? We activated row 3. So next, what do we have? Does someone want to say?
I guess it's a conflict because you activate row 7, so that 550 cycles.
Yeah, but what is the algorithm saying? I agree. It's if you activate 7, it's a conflict. But you have everything in the queue, right? In t equals 10, I have visibility of the queue. That's a trick, right? So you just don't go to 7.
Yeah, then we first row 3.
Correct. So because it's, as I said, first ready, first come, first served, right? That's why it's tricky when you do the alone calculation, because you need to imagine it as if I have a queue, have the visibility of the full state, and then I select the best order at which I can serve the request. Not the best, the first ready, first come, first served order at which I serve the request, which means that, as you said, it's 200 cycles, it's a hit for row 3. And then what do we see? We have row 7, row 2, row 0, row 8, and row 9. What is the problem here? That everything is a conflict. Whatever I do, no matter how I pick the order, I will end up in conflicts, which means I will spend 550 cycles multiplied by 6, which all in total is 3,900 cycles. So we calculated this for application A alone. Right now, we need to do the same thing for application B. So for application B, again, we will spend 400 cycles for the first. Does someone want to say how we do it for application B? It's a bit easier, I guess. So let's say we activated row 2. Then what do we do? You can say.
Yeah. Yes, and now the row 2s.
Correct. So how many of these are there? It's 4, right? So we for sure do 400 plus 200 multiplied by 4. And then?
And then one hit.
Correct. So which means that we activate then 3. We have a hit on 3. And then we have a conflict on row, which one was it? 4. And in total, we spent 2,500 cycles. So this finds one of the terms which we need, which is the bottom term. Now we need the top term. We need to actually execute right now application A. How we find the latency of executing application A while the application B is running in the system. How do we do that? With B. Any idea? Because basically, why is this more complicated right now? Because at the same time, you need to do application B, right? You cannot do only the application A. So in this scenario, we have for sure 400 cycles, right? Which we need to wait because of the precharge. It's precharged the row. We need to activate the row, correct? And then what do we want? We need to, what do we execute? So that's the key thing here. We need to open row 2 of B. Why do we open row 2? All the requests, application B, right? And then, as we can see, we have 4 requests for row 2. Do we charge these? From application B, I mean. Does anyone want to say? Yeah, you can say. Correct. So we need to serve the 4 requests from application B and then go to the row 2 of application A because this is not the older request. So we need for sure to pay here So what did we fix? What did we serve right now? We serve this, we serve this, we serve this, this, and this. And the question is, what do we serve next? We open row 3. Okay. To open row 3, we need to pay 550 cycles, right? Because we need to basically pre-charge and then activate a new row. We have row 3 here. And which one do we serve first? We serve application B, because it also has a row 3. So we need to wait for plus 200. This one needs to wait for plus 200 as well. And then what do? We do not activate a new row because we see that application A also has row 3 2 times. This one and this one. So we need to pay for 200 multiplied by 2 plus 200 multiplied by 2. And now it's a final request of application B, which is row 4. We activated, it's a conflict because we had activated row 3 before. And we pay another 550 cycles. So in total right now, given that we finished the requests of application B, we calculate the total latency, right? Which is 3,100 cycles. Now we haven't finished with all the requests of application A, and we need to finish them. And how do we do this? We see that we have row 7, row 0, row 5, row 8, and row 9. And currently the only row that's activated is row 4, which was the last request. All of these are conflicts because we need to open up a new row every time, which means that row A, the application A, will experience 5 more conflicts, which makes the total latency 5,850 cycles. Is it okay? You can see, right? Okay. Does anyone have any question on that calculation? Yep.
So my question is about how do you choose? So the algorithm says first ready, first come, first served. How do you choose which one is first ready? Which one came first? And A or B?
So first ready means it's basically first row buffer hit. So I had row 2, right? Here. I open it up in application B. Basically, no, let's put it in another way. I have row 2 and row 3, which are the older requests of each one of the applications. So first you ask, is there a row buffer hit? No, because the row is pre-charged, right?
Yeah.
Then you ask, which came first? Application B came first because the caption says it. It says that the requests of B are older, right? Okay. Yeah, it says it because it says that the memory requests of the applications at T0 are these ones, and application B has nothing served, which means that applications B's requests are older, for sure. That's how you choose, based on the age.
Okay, yeah.
And now the final computation we need to do, we don't need to do all the calculations. So the slowdown of A is equal to 508.50 divided by 3.9, which is 1.5. And the slowdown of B is 3,100 divided by 2,500, which is 124. Any questions on that? I mean that. Yeah, correct. It says it here. It says channel 0, bank 0. It will be written, basically. We're talking here about usually when you have these sort of streams, right? You usually refer to the same bank because if it's in different banks, it doesn't matter, right? Basically, the last question is with respect to that, you will see it. And then there is another question, which involves the Bliss scheduler. It says, if we use the Bliss scheduler for what values of n will the slowdowns of both applications be equal to those obtained with FRFCFS? Does anyone have any idea? Like, in which case the slowdown of the applications remain the same? There are two scenarios where this might happen.
I would say we are always below the 10,000 cycles, where the
So n is not 10,000. N is the number of consecutive requests that I receive from an application. So
what I was saying is, so the number of requests is never deleted. So because it said after 10,000 it will be deleted. So we have to count how many requests each of the applications are sending and see if well.
yeah, but we need to configure n, right? So we need to configure the number. So Bliss, what does it do? It sees a stream of requests. If for some reason the memory controller services n requests from the same application, then it starts slowing down this application. It deprioritizes it, right? The question here is different. It's not what you say. It's like, how big should be the n so that the slowdown is the same for both applications? That's different than what you say. Here, what you say tries to optimize a different thing. Yeah, the slowdown remains. That's not the question. The question is, how does the slowdown remain equal for the applications? Yes.
N should be 4 greater than 8. So that's 3.
Why 8?
The number of rows.
We have in
5.
Okay, that's correct, but not exactly. So one example is what you described. So we want to blacklist both applications. Basically, we need an n so that we can blacklist both applications. And this gives us the same slowdown, exactly. Right? And the question is, how do we blacklist both applications? We start by opening row 2. And then we open, basically, let me write it here. So we open row 2. And then application B opens row 2 one time, 2 times, okay, reads from row 2, 1, 2, 3, 4. Right? So in total, we serviced 5 requests from application B, right? If the n is larger than 5, which means equal or larger than 6, then we will not blacklist application B, which means that this sequence that we described before will hold. So your example is about not blacklisting. Okay, correct. So one scenario is then n larger or equal to 6. Right? Is that clear to everyone? That why you don't blacklist? Because in this scenario, row B will application B will never be blacklisted. With this means that application B will finish first. And then even if application A gets blacklisted with the n larger or equal to 6, then it doesn't matter because application B has already finished. You won't see this deprioritization in the actual stream. You don't care about it. But this is not enough to get the full points because there is another n that serves this as well. There's one specific n that gives the same effect, basically. So one is if both applications get blacklisted, right? How do we blacklist both applications? Because if both applications get blacklisted, the order remains the same because there is no one that has more priority than the other one. So these calculations will still hold true. And how do we blacklist both applications? Immediately. Correct. This basically does not blacklist, and this blacklists everything. Okay, is it clear to everyone? Yeah.
If n is equal to 1, wouldn't be also both blacklisted?
Let's see. You want the same slowdown, right? That's the thing. If you do not assume that both are blacklisted, then you might start with application A first. But if at n equals 0, both are blacklisted, you start with B. That's why you need to guarantee the slowdown is the same.
Okay.
Is it clear?
Yeah.
I mean, maybe you can find an n that guarantees the slowdown is exactly the same, right? But do not go into brute forcing the n. So let's go to the next one. So for what value of n, which is a blacklisting threshold, will the slowdown of A be smaller than 1.5? So right now we calculated here that the slowdown of A is 1.5 in this scenario, right? And the question is there a chance that this slowdown can be smaller than 1.5? So what would we need? You need to start your thinking and your response, because that's not an easy question. Why, like, what do we want to achieve to basically promote the request and prioritize the requests of application A? What is the way?
Yeah, I guess the reason why A is slowed down is because B has a lot of row buffer. So it will be prioritized. If you set the n low enough, it will increase the speed of A.
Okay, so in the previous answer, right, we find out that with n equals 4, or with n larger than 6 or equal to 6, things are the same. The slowdown is exactly the same, right? Which means that the slowdown of A for n equals 0 and n larger or equal to 6, it will be 1.5, correct? And you're saying that with an n equals 1 up or 5, 1 to 5, there might be a chance that the request of application A will be, that the application B will be deprioritized, and then we will prioritize A. Okay, let's see why this is not true. So let's say that we pick n equals 1. As your fellow said. So row 2 gets activated, right? We blacklist. And then we go to row 7, to row 2 here. What's the problem? This get blacklisted as well. And this will happen for any n from 1 to 5. Yes, it's the same thing. That's why the answer to the question is that it's not possible. It's not possible to find an n that does that and reduces the slowdown of A lower than 1.5. Why? Because whatever you pick from, so if you pick 4, let's say, right, still you will execute these 4, right? And it's the same thing. The moment you execute then row 2, let's say, and then you will execute row 3, and then you will blacklist again. So there's no way you will execute application A faster if you pick something from n equals 1 to 5. Why? Because again, both of them will be blacklisted. So the answer here is that this is impossible. In the exam, it would be good if you do it by hand. Try with 1, 2, 3, and 4 and see that it's not possible. The calculation is going to be easy anyways because you did it already before. So with n equals 0, we show that it's not true. With n larger or equal than 6, we show that it's not true. And then with from 1 to 5, we did the calculations, let's say, and it showed that it's impossible. Next question. So for what values of n will B experience the maximum slowdown it can possibly experience with a blacklisting scheduler? How would you approach this? There is a thinking behind it. It's not brute force. Of course, you could brute force, right? From 1 to 5, you see which one. One solution is clear on that. Like if you don't want to think, compute from 1 to 5. You pick the biggest number. That's it. Solved all the points. But if there is a way that you can try it or do it more efficiently. So if you pick, let's say, I will say randomly a number n equals 5. What will happen is the following. You will activate row 2, row 2, row 2, row 2, and row 2 here. And immediately, B is blacklisted, right? So what will happen next? You will service 5 requests from application A. 1, 2, 3, 4. Basically, 1, 2, 3, 4, 5, which means that application B right now, instead of activating the row 3, which would do in the initial program, right? It will right now activate, it will now right now wait until application A is deprioritized and blacklisted. And the maximum, the more it waits for application A to be blacklisted, the worse for application B. That's why the maximum number n equals 5 is the one who gives this. If you do it for n equals 3, then row A will quickly, application A will quickly get deprioritized. That's why you pick the maximum number, which doesn't give the equal slowdown. You pick the maximum, which is n equals 5. Again, it's the maximum it's a maximum time with n equals 5 that application B waits for application A to be blacklisted. That's why you pick this number. Of course, again, if you do it brute force and you check all the numbers and you find out the slowdown, the maximum slowdown, that's enough as well. So it's n equals 5. Maximum time for app A to be blacklisted. Any questions on that? Yeah, in general, these, even though the answer is really short, they need a bit of thinking. It's not straightforward when you see the question. And then the last one, which is the easiest one, in my opinion. What is a simple mechanism that we can use instead of bliss to make the slowdowns of both A and B equal to 1, 0, 0? And why? Any ideas?
Place the different rows.
Correct. So one of the ways is this one. So, but what is the problem with that? That's so you want to do interbank interleaving, basically, right? You want to put all application A in bank 0 and all application B in bank 1. If both banks want to send commands to the DRAM to the channel, what will happen? Will they see interference of 1, 0, 0? If they contend for the channel, right? Is there a chance that the slowdown is going to be 1, 0, 0? Yes, exactly. So that's why this answer is not 100% accurate. So how would you be sure that they don't contend for any resource?
Also different channels.
Yes. And how is this technique called? You saw it in the course probably. Yes. So we want to do memory channel partitioning. In this way, we have up A here has access to channel 0, up B has access to channel 1, and these go to different modules, let's say. Okay. Any questions overall on about this exam question? If not, I will continue with the next one.
This is perhaps one of the easier questions that you can find in the exam. This is about emerging memory technologies, and the first part you can easily solve it if you have attended the lecture and have gone through the lecture slides. So let's start with the first part. So if you're not able to see the some part of the question, please let me know. So the first part is on phase change memory, and we need to indicate whether each of the following statements is true or false. And if you give a wrong answer, then we subtract 1.5 points from each incorrect answer, and the minimum you can get from this question is 0 points. So the first question is data is written into the phase change memory by injecting current to change the magnetic polarity of phase change material. What do you think is the answer? Yes. Yes, exactly. So we inject current to change the phase of the material and not the magnetic polarity in PCM. So during multi-level cell PCM read operation, the time taken to determine the value of bit 1 is the same as that of bit 0. Any answers? True?
False.
Exactly. So here, if the resistance increases, then the sensing time is also it also increases. So with higher resistance, the sensing time is more. So that's the reason the time taken to read is not the same for bit 0 and bit 1. And the third question is in the same spirit. So MLC PCM has higher latency and energy consumption than single level cell PCM. Yes. So the answer is true because with MLC PCM, you have you need to use basically sense multiple resistance values, and that's how you that results in a higher latency and energy consumption. So the fourth question is PCM has lower endurance than DRAM because writes to PCM take much longer. Yes. Yes. Actually, the first part of the question is true that the endurance is lower, but then the reason that the question gives is not the right answer. Then it takes the same energy to write 0, 0 and as to write 1 into the PCM MLC PCM set. So the answer is false, because so 0, 0 and 1, 1 will involve set and reset operations, and the energy consumption of set and reset operations are different. So that's the first part of the question. So the second part is basically you need to do some math and get the answer. So we'll read the question first. So computer scientists at ETH have developed a new non-volatile memory technology, ETH-MEM. The access latency of ETH-MEM is close to that of DRAM, and ETH-MEM provides higher density compared to that of DRAM technologies. However, compared to DRAM, ETH-MEM has limited endurance. That is, the memory cell stops functioning after 10 to the power 6 writes are performed on the cell. And this phenomena is known as cell wear out. A bright ETH student has built a computer system using 1 gigabyte of ETH-MEM as main memory. And ETH-MEM exploits a perfect wear leveling mechanism, that is, writes are equally distributed over all the cells of the main memory. So the first part of the question is, the student is worried about the lifetime of the computer system she has built, and she executes a test program that runs special instructions to bypass the cache hierarchy and repeatedly writes data into the different words until all the ETH-MEM cells are worn out. That is, you write to the entire device and make sure that the device is worn out, and the system becomes useless. The student's measurements show that ETH-MEM stops functioning, that is, all the cells are worn out in 1 year. So we assume the following in the question. So the processor is in order, and there is no memory level parallelism. So everything happens sequentially. Each write request is fully serialized. There are 3 steps in each request: memory request from CPU to memory controller, then from the memory controller to ETH-MEM, and data write to ETH-MEM cells. So none of these steps can be pipelined. And it takes 5 nanoseconds to send a memory request from the processor to the memory controller. That is the first part. And then 35 nanoseconds to send the request from the memory controller to ETH-MEM. So ETH-MEM is word addressable, and this is an important part. Okay. So thus each write request writes 4 bytes to memory. And for ease of calculation, we have given certain hints. So 1 GB is equal to 10 to the power 9 bytes, and the question is to basically calculate the write latency of ETH-MEM, and the hint is that 1 year is equal to 3 into 10 to the power 16 nanoseconds. So so this question can be easily solved with a formula. So basically we need to this formula calculates the total time for the wear out of the ETH-MEM device, and that is based on the total number of writes that you need to perform for the entire device, and then how many times you perform the write for each to each cell. So that is that's basically the endurance part to the total time taken for, let's say, the end-to-end write latency from the CPU to the ETH-MEM. So here what we have provided is the total the time for the wear out, which is 1 year, which is also given as 3 into 10 to the power 16 nanoseconds. And total number of writes is basically calculated from the device capacity, which is 1 gigabyte, by the word addressability, or the granularity of writes. So you basically do 4 bytes to find the total number of writes that you need to perform across the entire device. And then this endurance is basically given in the question as 10 to the power 6. Yeah. So the memory cell stops functioning after 10 to the power 6 writes, or you perform the write 10 to the power 6 times. So, and then the total time is basically, as we saw here. So this is from time from CPU to memory controller plus time from memory controller to ETH-mem plus time for the write in ETH-mem. So 3 into 10 to the power 16 is equal to, so we have also mentioned 1 gigabyte is 10 to the power 9 divided by 4 into 10 to the power 6. So these values are already given. So you have 5 nanoseconds for the CPU to the memory controller plus memory controller to ETH-mem takes 35 nanoseconds. And what we need to find is the total write latency of ETH-mem. So this is, I'll write it as T write. So with you basically have to find the T write now, and here you T write is equal to 3 into 4 into 10 to the power 16 divided by 10 to the power 15, because I multiply these two minus 40. So this will be 10, and you get 120 minus 40 is equal to 18 nanoseconds. That's the write latency of ETH-mem. So the second part of this question, any doubts so far? So the second part of this question is ETH-mem currently works in multi-level cell mode, in which each memory cell stores 2 bits. And the student decides to improve the lifetime of ETH-mem cells by using the single level cell mode. And when ETH-mem is used in SLC mode, the lifetime of each cell improves by a factor of 10. And the write latency reduces to 32 nanoseconds. And what is the lifetime of the system using the SLC mode? If we repeat the experiment in part A with everything else remaining the same in the system. So I forgot to mention that if you don't provide all these steps, you don't have to give us the final answer in terms of, it would be nice if you provide this final answer, but because the math is also not very complicated. But please provide your steps, the steps for every question in this, so that we can give you partial credits if you're not able to do the math in time. So, so here the important parts of this question is that the lifetime of SLC is equal to 10 times the lifetime of MLC. And the write latency is 32 nanoseconds. So we go back to the previous equation again. And here what we don't have in this part of the question is basically to find this. So we again, so we find the T wear out. And here, so one thing you have to keep in mind is that here we have the student has decided to use the SLC mode, which means that earlier it was in MLC mode, and now the density of the capacity of the device reduces by half. So reduces to half. So now what was 1 GB will become 1 GB by 2. And you still have the 4-byte granularity and the lifetime or the endurance. So that increases by 10 times. So which means that it becomes 10 to the power 7. And then you basically have the same values for the CPU to memory controller transfer and the memory controller to ETH-mem. And then we also know the write latency of the SLC device, which is 32. So this is 10 to the power 9 into 10 to the power 7 divided by 8 into how how much is this? 40 plus 32, 72. This is 9. So 9 into 10 to the power 16. This is in terms of nanoseconds, but we also provide the hint that each year takes around 3 into 10 to the power 16 nanoseconds. So if you divide it by, so it's approximately 3 years. That's pretty much the question, the solution for this question. It basically depends on one equation that you need to know to find out the wear out time and the different write latencies.
Okay, this is the memory consistency question. A programmer writes the following 3 code segments, C code segments. She wants to run them concurrently on a multi-core processor called SC using 3 different threads, each of which will run on a different core, and the processor implements sequential consistency as we discussed in the lecture. Does anyone remember what sequential consistency? Because we need it for this exercise. I will repeat it. Okay, do you remember? I mean, Onur usually shows it this way. I remember it from the CMU course. So he shows the clock. There's something like a needle that goes to its thread, right? So imagine we have a clock, let's say, that picks at any point in time one instruction, and this guarantees that inside the same thread, I cannot see another ordering of the instructions. So one example is the following. So let's say that I have a needle here, and the needle has 3, let's say, options. It goes either here, here, or here. So what do? You start, let's say, with this one, and then it doesn't matter where you go, but you need to go somewhere, right? And then you go and execute something from here. And the needle changes and it goes here. So what does this guarantee? I will always see the ordering intra-thread. There is no way I break this ordering. That's why I can see the ordering from another thread, but I can see executed instructions from another thread, but intra-thread, I cannot see any sort of reordering of instructions. And the second question breaks this assumption, so that's why I explained this. I like this example that Onur brings with a clock. Clock, however he names it. So then, what does the question ask? We have these variables, A, U, C, V, W, which have been allocated in main memory. And the read or write to any of these variables generates a single memory request. The initial values of all memory locations and variables are 0. This is critical, the variables are 0. And we assume that each line of the C code segment of a thread is a single instruction. What are the possible values of variables U, V, and W after the program finishes execution? Explain your answer by providing the order of execution of instructions for every output. So the way you will approach this every time you see it is whenever you have a memory consistency question. So what are all the possible values that can occur in this occasion? So as you can see in the program, A is equal to 1 here, C is equal to 1, and here some jiggling is happening between U equals A, V equals C, which means that at the end of the day, we only have 2 values, right? 0 and 1. So the best way to do this is we create some sort of truth table, let's say, with all the possible values for U, V, and W, which means we start with 0, 0, 0. And then we ask the question, is it possible with sequential consistency to reach this result, 0, 0, 0? Yes, it is. Why? The clock starts with T10. We go here to T10, right? And we do U equals A. What's the A in the beginning? This has not been executed yet. A is 0, which means that UVW, in this scenario, U is 0. So the first one we executed is T10. What's the next one? We want to set V to 0. How do we do this?
T
Correct. And then we want to set W to 0.
T to 1.
Correct. This is one combination, right? And imagine you need to do this for all the combinations. Then we have 0, 0, 1. In 0, 0, 1, again, U the same, T1, 0. V the same, 2T0. But then W changes here. We need to set W to 1 somehow. We need to find a way. And the way is, yes?
T0, 0.
Correct.
And T to 1.
Correct. Do you understand why? Because we need to execute first A equals 1 and then execute T to 1, which sets W to A. A has been committed, it has been written. And then you go and set W to 1. Next scenario. This is a really boring exercise, which you will need to do. 0, 1, 0. Again, U is 0, so you first need to execute T1, 0. And then after T1, 0, somehow you need to figure out a way that V is set to 1. And the only way that V is set to 1 is if you execute T1, 1. You need to set it to 1 and commit it. And then we execute T2, 0. And then we execute T2, 1. And then T0, 0. I mean, even if you don't write T0, 0 here, it's fine. Then we have 0, 1, 1, which is again T1, 0. Then we need to set V equals 1. The only way for this to happen is okay. T0, 0.
Can you get...
Oh, sorry. Yeah. So we set with T1, 0, we set U to 0. And then we need to set V to 1.
T1, 0 and T1, 1.
Correct. T1, 0 again. What did you say? Sorry.
I'm not seeing the last line.
Oh. How can I? Yes. Yes.
And then T to 0.
Okay. And then
T0, 0 and T to 1.
So be careful here. You can do the T0, 0 at any point in time. Just make sure it's before T2, 1. That's the key thing. And after T1, 0, so that the U is not set wrongly. What's your I don't have much space because I explained the clock. Yeah. So I have here 1, 0, 0. How do we end up with 1, 0, 0? We first need to execute this. And the question is why? Because we need to make sure V is 0, basically. So we execute T2, 0. and then we execute T21. And right now we're sure that V and W are 0, regardless of what will be written later, right? And now after T20, T21, we execute T00, which sets A to 1. And after A is set to 1, we execute T10 and T11. Okay, so here we need to write first. We need to show the scenario where we write first 0 to W and V, and then we show the U, which changes based on the A. And then we have, I will continue down. Basically, no, I will continue here and then I will go down. So here I have 1, 0, 1. You can see now like this. And in 1, 0, 1, we need to execute first T20, which sets V to 0. And then what changes here? If I do T21, then W will be set to 0, which is something we don't want. So we need to execute first, then T00, and then T21. And then T11. And this is then the most interesting example is U, V, and W equals 1, 1, 0. Can someone argue why this is not possible? I'll show you the instructions again. Again, we want 1, 1, 0, U, V, W. Yes.
Because to have V equals 1, we must execute T11, but before executing T11, we must set U to 1. So by setting U to 1, we must set W to 1.
Which breaks the order, basically, right? Correct. So this is not possible. This is an impossible scenario. And why it's an impossible scenario? Because the next question asks this, basically. What are the possible finite values of variables U, V, and W after the program finishes when you have a weak consistent model where you can reorder instructions? So, but you need to, which is not possible basically using the sequentially consistent memory model. What does this ask? In the sequentially consistent model, some of the outputs are not possible. And right now, some of the outputs in the weak consistency model are possible. So these which are now possible and show how they are possible. So we need to find out UVWs that end up in 1, 1, 0, which is the only one not possible in the sequentially consistent output, which are possible right now in the weakly consistency. We have two scenarios where this is possible. So we might have basically intra-thread ordering right now. This clock key doesn't work anymore. So we have T21 executing first, because that's how it is. We execute first W equals A. And that's how we can write W0. Then we execute A equals 0, A equals 1. Oh, you cannot see. Okay. So it's T21, T00, and then you execute T10, T11, and T20, which means we first execute W equals A. W takes the value of 0, right? And then we need U and V to take the values of 1. So how does V take the value? How does the U, take the value of 1? We need to execute T equals T00, which is A equals 1. So then we go to T10, right? Which means that U is set to 1. And then we need to set V to 1 as well. And how do we set V to 1? With T20. There is no other way that C equals 1 and then V equals C. There is no other way. What did we do here? We broke basically the ordering of these two instructions, right? Which breaks the sequentially consistent model. Is it clear? Again, you need to find ways to break the order. Things can be written intra-thread with different orders, right? That's a very quick consistency model. That's one scenario. Potentially, you can find more scenarios here that lead to the same example of 1, 1, 0, but you will get the full points if you give this one. Sorry, yeah, if you give only this scenario, you will get the maximum points. It says here that after several months spent debugging your code, the programmer learns that the new processor includes a memory fence instruction in its ISA. And the semantics of the memory fence is as follows for a given thread that executes it. It waits until all preceding memory operations from the thread complete in the memory system and become visible to other cores. Ensures no memory operation from any later instruction in the thread gets executed before the memory fence is retired. And it asks, what are the minimal changes should the programmer make to make your program to ensure that the possible final values UVW on weak consistency are the same as the ones in part A on sequential consistency? Another indirect way of asking is, how is it possible that I have the weak consistency model that disallows this? I should not allow 1, 1, 0 by putting fences somehow. So the question is, how do I do this? How do I change my code to, where do I place the fences so that they do not allow this?
Find where the memory consistency breaks in order to produce the resulting bit. Here in the example in the thread 2, between to 0 and to 1, and then put the fence in between.
Correct. So you want to avoid completely this intra-thread reordering, right? And the way to do this is by placing the memory fence in between T02, T20 and T21. So you need the memory fence here. There is one more case, which I didn't show before because, as I said, you will get the full points for this one. But this is not the only way to reach this. So I might have a memory fence here and still be able to break the consistency. I will show you right now how. So I can execute T11, which is C equals 1. Then I can execute T20, which set V to 1. So I executed this, C equals 1. Then I executed V equals C. So right now, V is equal to 1. And then I execute T21. I execute W equals A, which means that W is 0. So we have V equals 1, W equals 0. And then we need to make the case that U is equal to A. So we execute T00 first, and then U equals A. So we find another way to reach the same example, right? T20, T21, T00, T10. This is another example, which is, okay, it's optional for this question, right? But if you do not find this, then you cannot answer this one, basically. So what do? We need two memory fences. One here, as we discussed, and we need a memory fence here as well, so that we do not allow C equals 1 before U equals A happens. Is it clear? If you have any questions, now is a good time. This is pretty straightforward. I mean, it requires lots of maybe, combinations, but it's not a hard exercise.
I will also start by saying that this is one of the easy questions. So maybe it's smart to check all questions first and, choose the ones that are easy and that are easy to gain points. Okay. Order these. let's take a look at the question together. So for this question, we have a system with 4 byte addressable processors, as you can see here. And each of these processors has private L1 caches with these properties that we will talk about in a second. And basically what we're interested in is the coherency, cache coherency of these caches, coherence of these caches. So yeah, here we have a note. It says that when we write to a cache block, which was in the S state, shared state, the block will transition directly to M state. So this is good to remember during the question. So here you can see different instructions will be executed in different processors. I hope that you still remember what sequentially consistent is. But for this question, what we're interested in is basically we cannot reorder instructions that are executed in one processor, but we can basically change the order of different instructions from different processors. So they can be executed in different orders, but we cannot basically reorder 0, 1, 2, for example. And what we have here is the basically final state of these caches after these 9 instructions are executed. And we don't know like in which order they're executed. We are trying to basically figure out what happened and in which order they were executed so that we got this state. The first task is basically to determine what was the initial state. But we will basically do both like this item and also the ordering together so because like they're already related to each other. Okay, so what I would first do when I see this question, I would first figure out how to index these caches. So like I said, we have some properties here regarding these caches. So we know the total size and also we know the block size, which is 64 bytes. So this gives us the information that we have 4 different sets in each of these caches, as you can see here as well. So I would take one of these addresses. Let's take the first one. Maybe I can another paper here. Yeah. So let's take the first one and write it in a way that we can see the set bits so that we know like which set we will write that cache block to. So this can be written as, oh, okay. And yes. So since we know the block size, we know that these 6 bits are used as byte offset, and basically we won't be using these for this exercise. And we know that since we have 4 sets, the next 2 bits will be the set bits. So for each of these addresses, we need to determine the set bits so that we know where to put that basically cache block in the cache. So fortunately, I already did that. Yeah, basically what you need to do is take the first 2 bits of like this and this and this. They are not aligned, but I guess you can figure it out. And basically the rest of the address is used as tag. So we know that the first 3 numbers you see here or letters basically will be the tag. So right. Okay, so we have the instruction numbers here, and these are the processors. So we know that these will be executed in some order that will result in this final state. So let's take a look at each set one by one and try to figure out what happened. For set 0, let's see which instructions we have. So okay, maybe I can reorder these a bit. Like, I suppose this is okay. Yeah. Okay, for set 0, what we have is this instruction here for processor 0, which is the instruction 1. And we check the other processors and see another instruction that is from processor 3 will be also executed, which is the instruction 7. And this instruction 1 is a store, and the other instruction is a load. And both of them have the same tag. So, yeah. So what we see here in the final state is all of these actually caches have the same tag, which means that they basically end up having these tags, all of them. And when we check the states, P0 and P3 has shared state and the other ones are invalid. So, okay. Can you guess like in which order these two instructions were executed such that we had both shared states? Yes, please.
The store is executed first.
And then the load.
Yes.
Because
So-
the load.
Yeah.
The load degrades from the modified state to the shared.
Yes. So if it was the other way around, if the store was the latest one, we would not have shared because it would invalidate the others, right? It's basically the explanation in the other way around. So first the store happened and then load happened. We can say that instruction 1 executed first and then we executed 7. And basically that's the ordering. And when we think about the initial states, so P0 and P3 both had something to do with these. Basically, they brought these cache blocks into their caches. So we don't know what was the initial state for them because it would replace it anyways, right? Because we executed something. So because of that, their tags will be X, which is used to show we don't know, like the initial state of that tag field is unknown. And the states could be anything, right? Because it could be any other cache block that was written. It could have been an exclusive cache block or anything. So we will write all possible states for these because basically it could have been anything. And for the other ones, what we have as a hint is that they already have these tags, even though we didn't do anything related to these. Basically, we don't execute any instructions related to this. So they should have, in the initial state, have these tags. So that they were not changed basically by our execution. And we again don't know the states because basically in the beginning, any of these like processors could have done anything to it, write back to it, or I don't know, they could also read it both and have shared states. So again, all states are possible. Okay. So let's do the same thing for set 1. When we check our instructions, we see that set 1 is used here. So the first one is the instruction from processor 1, which is the 4th instruction. And from P2, we have 6th instruction. And from P3, we have the instruction 8. And when we check what are these, this one is a load. And this one is a store. And this one is also a store. And again, the tags are matching. So we don't need to think anything about the tags at this point. So when we check the final state, we see that, again, all the caches have the same tags, and the states are invalid for 3 of them, except P2, which is modified. So can you guess what happened here? Again, similar to before? Yes, please.
Yeah, I guess the store in P2 must be the last one because it will invalidate all the others. but about the other order, we can't really.
Yeah, basically, we know that this is the last one because it's modified and the others are invalidated. But before that, we don't know what was the state, so we cannot know which instruction was executed first, 4 or 8. So what we know is, oh, you were not seeing it fully, I guess, but yeah. So 4 and 8 executed in, I don't know, like an unknown order, and then we executed 6. So when you think about the initial state based on this, well, okay. So yeah. Basically, when we think about the initial state, we know that these 3 processors used this, like brought these cache blocks. So we know that their tags could have been anything again. So what we will do is we will fill out their tag fields. Let me quickly check. Yes. So except P0, we know that this could be anything. These tags could be anything. And similar to the one that we showed just for these in set 0, their states could be anything again. Can you guess what was the initial state for this one? The tag and the state? No? Yeah. Okay.
I guess the tag should be 001 because it would not have been changed.
Oh, do you mean 001 or maybe you yes. Okay. Yeah. It's not very visible. Yes. Okay. That's correct. And what about the state?
It could be anything because it would have been invalidated by the.
Yes. That's correct. Okay. So let's do the same for set 2. And here for set 2, we have this, and this. P0, instruction 0, P1, instruction 3, P2, instruction 5. And this one is a store. This one is a load, and this one is another load. So again, the tags all match, so we don't need to think anything about it. Let me show you the final state. So we know that when we check the final state, we are checking this one. Or maybe I should use. Let's try this one. Okay, we are checking this. And maybe it's good to write the tag here also, since you cannot see it. Okay, so what we can see from here is that in the final state, we have 2 shareds here for P0 and P2, and the others are invalidated. So again, can you guess what happened? In which order did we execute these?
So P1.
Okay, so this is the first one.
Then there was a store of P0 and then a load of P2.
Okay, so 3 executed first, and then 0, and then 5, right? Yeah. Okay. So this is again very similar to what we have done. And when we think about the initial state, let's go there, and oh, maybe you need to also see this. But can you guess the initial tags and states for this one? So it's again very similar. We have a hint here. So all these like P0, P1, oh, you cannot see. So P0, P1, and P2, they use this, basically they brought that cache block, so we don't know their tags, and it will be again X for these. But for P3, we actually didn't do anything in that processor, and the tag was already here. So it should be in the initial state as well. Since we don't know like these cache blocks and what happened to them, that's like the same with the rest. It should be, all should be basically correct, or yeah, all could be there basically. And for this one, since what we know here is that it's invalidated, and since we did a store to that one with the instruction 0, we don't know what it was initially. So again, the all states could be anything. Okay, so we are almost at the end. And let's take a look at set 3. We only have one instruction, which is this one from, oh, you cannot see it. Yes, this one from P0, instruction 2, and it's a load, and that's pretty much it. So we don't do any ordering for this one. And let's check the states for this one. So, wait, okay. We also need the tag for this. Okay. Right. So we are doing this one. Let's check the final states. So this is shared. This is invalidated and shared. We know that we basically loaded this cache block to P0, but we didn't do anything in here. So basically the cache block was there, right? So based on that, can you guess what would be the tag and state for this one only? Like this blank spaces. Yes, please.
The tag would be the same.
Yes.
But the state could be either modified, like exclusive or shared.
Mm-hmm.
Then when you did the load, it just collapses to shared.
Yes, that's correct. So could it be invalidated also, like, or? Yes.
No, because no one would load it back to the memory, to the share position.
So we exclude only invalidated, and these could be basically the states for this one. Okay, and basically this one is the easy one because we load it to this cache, and we don't know what the tag was before, and we don't know the states. But the other two are basically the same state, right? Like, can you guess what was their initial state and tags? Please.
The tags were the same.
Yep.
So I think the state was invalid.
Yeah, since we didn't do any stores, we wouldn't be able to invalidate them. So they were, even in the beginning, invalidated. Yes. Right. That's it for this task. And for the next one, the question asks, in what order, in what order did the memory operations enter the coherence bus? Show your work. So as you can imagine, there are different like correct answers for that. What is important in this question is that we remember it should be sequentially consistent, so we should not reorder instructions from the same processor. But we basically created this order between different instructions from different processors, right? So we know that instruction 1 was executed first, and then 7 was executed from set 0. And then we know either 4 or 8 was executed first, and then the other. And then we executed 6, which was from set 1. And then from set 2, we basically gathered this information that instruction 3 was executed and then 0, and then 5. So we can simplify these. Basically, we can reorder, we can determine the order of processors basically by just writing the processors instead of instructions. So I will just do that. So instruction 1 is from processor 0, and then 7 is from processor 3. And 4 and 8, so instruction 4 is from processor 1, and 8 is from processor 3. And then 6 is from processor 2. And for the other one, 3 is from P1, 0 is from 0, and then what is the other 5? 5 is from P2. So from this, you can also match them and then create one global ordering, which is P1, and then P0, and then P3, and then P2. Basically, this gives us the order based on the, maybe I can show them both. Yeah, basically you can just write the instructions in order based on this. So the answer should be 3, 4. One of the correct answers should be 1, 2, 3, 7, 8, 5, 6. Okay. And the last item is basically, it asks what is the minimum number of writebacks needed for this instruction sequence. So for this question, you need to think about the cache blocks that are used after they are modified. And basically, we had 3 occasions like that. The first one was 0. Wait a second. The first one was 0, and then instruction 1, and then instruction 8, which I can also show from here. Oh, yeah, no, I guess we can also show from here. So these are the store instructions that are basically followed by other instructions that uses the same cache blocks. So these 3. Okay. Do you have any questions?
This question is also a bonus, but I mean, in the end, doesn't matter. You can check all the questions and start with whatever you prefer. So the question is about 2 topologies, and first we need to make some comparison among them. So we have one bidirectional ring, and another topology is hypercube. So, and in our system, we have 2048 processors. So the first question asking, let me put the question actually. Much better. So we have 2048 processors. So the first question is asking, calculate the number of network links for each of these 2 topologies. So whenever we are dealing with a regular graph, one easy way to calculate the number of links is actually when we know the number of vertices, and then we know also the degree of each node, we can easily times the number of vertices to the degree of node divided by 2, because we don't want to count each link 2 times, basically, right? So in ring, basically we have 2048. We have 2048 nodes, and the degree of each node is actually 2 for ring. So times 2 and then divided by 2. So in the end, we have 2048 links for ring. In hypercube, number of vertices is again 2048. And what's the degree of each node in hypercube here?
Log n.
Sorry?
Log n.
Yeah, exactly. Log 2048, which is 10.
Yeah.
Because in hypercube, we always need we need to formulate it as 2 to the power n. And when we have 2048 nodes, it's going to be 2 to the power 10. Then basically n is 10. And then we have n neighbors for each node. So then the answer would be 2048 times 10 divided by 2, which is, I mean, something. You don't need to also calculate the final result. Yes? Oh, yeah, sorry. True. My bad. Thank you. Yeah, it's 11. Okay, so in part B, asking about calculate the maximum routing distance between the network. Basically, we are asking for network diameter. So I think you have already seen the definition of or calculation of network diameter in the slide. So for ring topology is when we have n vertices in a ring, the diameter is actually n over 2. So the diameter for ring is 2048 divided by 2, which is 1024. And for hypercube, basically, usually the longest distance is from between the two nodes that you need to basically, you have difference at all bit positions. So for example, if we consider a node that we have all 0 in address, the longest distance would be the node with all 1, basically. So we need to fix the distance at every step. So in the end, we need to take 11 hops to reach to the destination. So for hypercube is 11 hops. Is it clear? Okay. So in part C is asking, assume a network link can be faulty. So for each topology, what is the minimum possible number of faulty links that are needed to make at least one processor unreachable from any other processor? So basically, how many links we need to cut such that the network is not connected anymore? Any idea for ring? 2. Yes, exactly, 2. By cutting the one basically link, we're gonna end up having array topology. And then another link, when we cut it, then the ring is not connected anymore. What's the number for hypercube? Yes. Yes, exactly. As long as we have one, I mean, yes, exactly. So because each link, each node has 11 connection to other nodes, right? So in order to make sure that this node, sample node, doesn't have any connection to other, we need to cut all these 11 edges or 11 links. So the calculation is 11 for hypercube. So the first part of this question is done, which was, I think, pretty straightforward. But the second part is, it's complicated. Okay, so from our calculation in the previous part, basically we realized that hypercube is, the performance of hypercube is much better than ring, because so the diameter in hypercube is 11, while in ring is 1024. However, the cost of hypercube is high, right? So you realize that the cost of hypercube topology is not acceptable for connecting 2048 processors. After a lot of brainstorming with your colleagues, you come up with the nice idea of combining ring and hypercube topologies, such that each node of an n-dimensional hypercube topology is replaced by a bidirectional ring topology with n nodes. So basically, we have several rings, and we connect these rings in a hypercube manner. So you name your topology as a cube-connected ring with the following formulation. So we need this formulation to understand how we can make this topology. So basically, the cube connected ring of dimension n is a graph of n times 2 to the power n nodes. So this is very critical here. Each node is represented by pairs of x and y, where x is between 0 and 2 to the power n, and y is between 0 and n. Basically, x represents the position of that node in the hypercube. That's why we have this 0 to between 0 to 2 to the power n, and y is the position of that node in the ring, basically, right? And that's the reason it's between 0 and n. So each node x and y is connected to 3 neighbors. So the degree of this network is actually fixed, 3. And each node has 3 neighbors. So the 2 first neighbors are actually neighbors that we have in the ring, right? And the third neighbor is actually the neighbor that we have in the hypercube. So x and y is neighbored by x or 2 to the power y and y, basically. So this is important to realize. Okay. Any question about the formulation of this topology? Okay. So in part D, we are asking, draw the cube connected ring topology for dimension n equals to 4. Clearly show the nodes, addresses, x, y, and the links. So when we have n equals to 4, our topology has 4 times 2 to the power 4 nodes, which equals to 64. So you don't really need to draw all these 64 nodes and show all the connection. That's going to be a lot of huge overhead, I guess. But at least you need to show some connections, and because there are many repetitive patterns, so you need to actually mark them and summarize the answer, basically. So, okay. So since we have rings of 4 nodes here in a cube connected ring, I will make something like this. So this is, for example, one ring. There is also another ring here. Another ring. And another ring. And so on and so forth. So then we need to basically address them. I will start, for example, consider this ring has x equals to 0. So it's going to be 0, 0, then 0, 1. This should be 0, 2. And this should be 0, 3. This also is 1, 0, 1, 1, 1, 2, and 1, 3. This is 2, and this is 3. No, sorry, actually. Better to, in order to, I mean, you will realize how to address them, because otherwise, so your drawing is going to be super mess if you don't, if you, for example, name this one as 2. Better to start this one as 4, actually. But I will let you know why. And this one should be actually with 5. I mean, there could be also some other ways of drawing it. So in the hypercube, I mean, in the cube connected ring, each node has 3 neighbors. So we already actually showed the 2 neighbors, but there is also another neighbor which is happening in the hypercube. So for 0 and 0, which is x and y, the third neighbor is actually 0 XOR 2 to the power 0, which is 0 XOR by 1. The result is 1, actually. and then and y, which is 0. So 0, 0 is actually connected to 1 to 0. So this is a connection, the hypercube connection for this one. For this one, 0, 1. Yeah, better to go with this one because I don't have it. So for 0 and 2, the XOR of 0, so we need to calculate the XOR of 0 by 2 to the power 2, right? So 2 to the power 2 is 4, and 0 XOR by 4 is 4. So this is gonna be connected to this node actually, right? And for this one, so for this one also, we need to connect it to basically the node that has address. We can actually draw it. So if we call it, put it like 2 and 1, 2 and 0, 2 and 2, and 2 and 3. So for this node, I will just calculate. So the neighbor of this 0 and 1 would be 0 XOR 2 to the power 1 and 1. So XOR of 0 and 2 to the power 1 would be 2 actually. So this is gonna be connected to this node. And this node is connected to somewhere down actually, because it's gonna be, yeah, to 8. So you need to also draw another one down here, for example. And this is 8, 3. So this node will be connected to this one. Is it understandable? Okay, so I mean, to my sense, if you show something like that and show some connections and make it clear, you don't need to repeat more. Basically, you will get the full mark. It's impossible to draw it for the whole thing. Okay. Any question? But if you are interested to see the full picture, is something like that. So the next part, we are asking some numbers for this topology. So we are asking about the number of links, network links needed to connect these 248 processor. Now we want to use this cube connected ring for our example that we want to connect 2048 processors. So we are asking about the number of links for that. So the trick here is that you need to find an n number, which in the end, n times 2 to the power n is equals to 2048. So, I mean, you can just do it like try and error, and n equals to 8 will result to this number, basically. Right? Okay, so now that we know n is 8, we should calculate the number of actually we didn't need yeah, we don't really need to calculate n here, because there is also another easier way to calculate the number of links. So we have 2048 nodes, and the degree of each node is actually 3, right? Because each node has 3 neighbors, divided by 2, which is something. But it's good that we also calculate n here, but we don't really need it.
We need it for the next question.
I guess so, yeah. So calculate the diameter of a cube connected ring topology that connects 248 processors. So before, in order to, in the end, again, the definition of longest path in this cube connector ring, you need to combine your understanding of ring and hypercube. So basically, the destination node should be the one which is farther in the ring and also farther in the hypercube, right? So for example, if your so n is equals to 8, if your destination is, if your source, for example, is 0 and 0, you want to have a destination as, so from 0, the longest one is a full one, right? Because x is the position in the hypercube. So since should be actually 8 bits and full one, which is 255, I guess, right? Yes. So this is the x of destination in order to reach to the diameter. And for the y, which is the position in the ring, you need to find it. I mean, this needs some try and error, but usually starting with the number in the middle in the ring is makes sense, basically. So then you need to think about how you can actually route in this topology. So this is the figure for n equals to 4, but the idea is similar. So when we want to route a packet from source to the destination in this topology, we need to take, we need to go, for example, one hop in the hypercube. Then if it again take this hop in the hypercube, we will get back to the previous position, you know, because, for example, from here, I take this hop to this node. So this link is actually in the hypercube, right? So if we take this, if we want to keep continuing in the hypercube, we cannot actually keep continuing because we will get back to the previous node, right? So we always need to get one hop to the hypercube, then one hop in the ring, then hypercube, ring, hypercube, ring, hypercube, in order to reach the destination. That's the key idea, basically, in order to design a routing algorithm. Yes?
Isn't it possible at some time to import the ring and the hop in the hypercube?
It is possible, yes. That could be also. But in the end, you need to, I mean, sometimes you may not, you may add more hops as needed, basically. So that's important that you don't calculate, you know, the higher number of hops. But I guess overall, it should be possible that, I mean, it is possible, but we should be also careful about the number of hops that we are taking. Yeah. So, yeah. So here we need to start with our node, which is, for example, 0 and 0, and then basically put all the nodes that we are visiting in order to reach the destination. So the next one would be, so we first want to, for example, take a hypercube pass. It's gonna be 1, 0. Then we can take a ring pass, 1, 1. And then we take the hypercube pass. So the neighbor of 1, 1 in hypercube is 1 XOR 2 to the power 1, which is 3, actually. So it's going to be 3, 1. Then we take one ring pass, which is 3.2, 3, 2. Yes, exactly. And then from this node, we will go to hypercube line, which is going to be 7, 2. From this node, we're going to go for a hypercube pass. Sorry, ring pass, which is 7, 0, 7, 3. Then we take another pass in the hypercube. One way of calculating that is also making a sum. You don't really need to make XOR. So that XOR equation is there because of the overflowing. But if you don't overflow, you can easily just sum. So 7 adding by 2 to the power 3. So 7 by 8 is 15, basically. So 15, 3. And then we go another one in ring. So now you can see actually the y in this node is actually equals to the y of destination. So we would love to actually don't change y anymore and just go to in the x dimension, but it's not possible, unfortunately. We really need take at least one link in the ring such that we can move forward to the hypercube. So okay, so after this we will go another one in the hypercube, which is 15 plus 2 to the power 4, 16, 31. Then we go another one in the ring. Then we go another one in the hypercube, which is 63. And then another one in the ring. Another one in hypercube. Another one in ring. Now we should go back, basically, right? Or do we? I think it's gonna be similar, but yeah, exactly. We need one more to go to exactly. Yeah, otherwise we couldn't go to 255. So we need these 7 actually here. Make sure that we go to 255. Okay, now we go to one link to hypercube, which is 255. Okay, now we are in the final ring. The rest is easy, actually. Okay, so then you need to count the number of hops, which then is going to be 18. So yeah, in last year exam, many students, they solved the first part, but they didn't try the second part. I mean, there were some students that they did it correctly, actually, but not all. Any question? Okay, so we're gonna, I guess, next session will be the exam. Our exam will be in the same room. Our lecture room. We have a hard stop at 4 p.m. So make sure that you are ready in the exam room early enough, because we want to start exactly at 1 p.m. and finish by 4. So this is really important. All the materials that we have covered in the slides, the course is can be the exam material. We also presented many cutting edge research. You don't really need to basically know the details of all these works, but make sure that you review them, because there could be also some questions asking fundamental things or high level things about those works as well, including the papers that we covered yesterday also. So, the questions gonna be simple. They are not asking detailed mechanisms and detailed results, but the overall understanding of these works is needed in order to solve these questions. Any question you may have for the exam? Yes.
What materials are we allowed to use in these calculators?
So a calculator is not a load, but you can bring 6 pages, A4 handwritten pages for your notes if you want. So you can have that, but calculator is not a load. You don't really need to calculate as well. I mean, as Gerald also clearly mentioned, whenever you have calculation, just make it clear and leave it there. I mean, you don't need to calculate the final result, basically. Yeah, I will send an email and clarify all the basically details about the exam, I mean, logistics but yeah, beyond that, do you have any other questions? Okay, sounds good. So yeah, see you all next week for the exam day.